Hello. In this video, I will explain what constant velocity is and demonstrate it with a real-life experiment and a computational model. Later, we will be looking at the differences between the two models and extend our discussion to hypothetical questions. Let's go. This is Newton's second law. It states that the rate of change in the momentum of an object is equal to the net force applied to the object. That can be summarized in this formula. By doing a little algebra, we can arrange the variables in this manner. In our experiment and computational model, we will assume there is no net force acting on our body. This will result in a constant velocity, meaning the object will cover the same distance in the same direction in equal intervals of time. Here, we have our experiment set up in Tracker. I have used a yo-yo of circular shape to minimize friction. It was 5 centimeters in diameter and 50 grams in mass, both of which are irrelevant to the formula and the discussion. I have set the conventional direction for the axis, the right-hand side being the positive x-axis and the left-hand side being negative x-axis. Here we go. We treat the object as a point object and track its center of mass's position for each time interval. The object is moving in the negative x direction. Since we assume there are no net forces acting, we can also assume that the velocity is going to be constant throughout its journey. For that, I took the first two position points and I calculated the velocity, and it turned out to be minus 0.52 meters per second. As I said, we can assume that this number is going to be constant throughout its journey. Now remember, because of minor opposing forces like friction, the velocity will keep on decreasing slightly till it reaches the end. I will be using a computer simulation to replicate a similar situation of constant velocity. We will be assuming the net force is 0 again, which I did over here, and there is no drag for demonstration purposes. The code will iterate for every 0.01 seconds and update the velocity and position each time, as it's happening over here, until the time reaches 1.379 seconds, which is the time the yo-yo stopped rolling. Here, I set the ball mass to 80 grams, as I said before, and I set the ball's velocity vector to minus 0.52 meters per second. This is the value which I got when I measured the time taken by the ball to travel between 2 points in my earlier experiment, the one I did in real life. And if I run this is the simulation I get. As you can see, the velocity is constant at minus 0.52 meters per second. Here are all the iterations of position and time in my computer simulation. And here are all my iterations of positions and time intervals of our real-life experiment. If I scroll down below, here is the graph when I plot a position versus time graph. The red line is the computer model's velocity, and the blue dotted line is the experiment's velocity. If we take a look at both the lines, it seems the experimental model has a slightly higher magnitude of velocity than the computational model. This is generally not the case, as due to minor opposing forces such as friction, the average velocity will be slightly less than the initial velocity. This, in most cases, will cause the computational model to have a greater velocity than the experimental one. The differences appear quite minimal, and as far as I know, there might have been a few human errors while marking the center of mass in Tracker. There was also an abrupt frame jump in the video as observed over here. If I could just play back, notice how in the middle there is an abrupt frame jump, which is something beyond my technical expertise, so I can't fix it. This causes the graph to momentarily get steeper, and from there it runs parallel to the other line. See, at this point it gets steeper all of a sudden, and it just runs parallel to the other line. These issues might have caused the difference between the two models. Now, moving on to some possible questions. What will happen if I flip the axis? meaning if I interchange the negative and the positive x-axis. The magnitude of the velocity will remain the same, but the direction will be in the opposite direction. The graphs will also be reflected along the x-axis.
Is it possible to know the individual pushes and pulls acting on the object? No, it is not possible to know all of the forces acting on the object. Newton's second law only tells us about the net force, and unless we already have the knowledge to account for and calculate all the external forces, it's impossible to say how many forces are acting. Since the net force is zero, the one thing we can say is that all the external forces, no matter how many, are all canceling each other out. This concludes my demonstration of constant velocity using Newton's second law. I will provide all the necessary links to my works in the description below. Thank you for watching.